Kiser.
Hey, good morning. Good afternoon, Steve. How are you?
Good, thank you, Jeff. How are you?
So, by way of introduction for everyone, I'm Jeff Leeder. I'm a senior director in our National Security Space Division here over at Redwire Space. And I have the extreme fortune to be joined on the stage by Steve Kiser, someone who I've served with in the past in uniform and have the extreme fortune to serve with again in industry. So, Steve, introduce yourself a little bit.
Thanks very much for that, Jeff. As Jeff intimated, Steve Kiser, career Air Force guy, spent 21 years in uniform, some of that doing space work at Vandenberg, then Air Force Base. Subsequent to my Air Force career, I did about 10 years of work for the Department of Defense as a tech scout, and looking at a variety of things, kill chain, space architecture, sensors, that sort of thing. It worked as running a P&L at a mid-tier defense contractor, and now I'm serving as the CEO of Phase 4, where we are focusing on space, in-space mobility.
And we're fortunate to have Steve as part of our team on a strategic collaboration agreement that we've got. One thing I would like to say for everyone is that we are live streaming this on YouTube at our @Redwire Space channel, and it's also available for playback if you'd like to re-watch any of our episodes today or all week actually. So before we jump in, one of the challenges when we start talking about technical things is the community may not have common terms of reference or understand exactly what we're kind of talking about when we talk about Hall effect thrusters, or we talk about a power propulsion management unit. So Steve, would you mind taking just a few minutes and identifying kind of the key elements that we've got on the table over here of what actually comprises our Valkyrie Hall effect thruster?
Absolutely. It's important to understand that there's different ways to move a satellite once it's already in orbit. The two most common categories is chemical propulsion and then electric propulsion. We fall squarely in the electric propulsion category. And then within electric propulsion, there's different ways of creating the plasma that creates the thrust. Radio frequency, FEEP, electrostatic spray. The most common type is Hall effect thrusters. Hall effect thrusters, that technology was developed by the Soviets really in the 1960s. We got access to that technology in the 1970s. NASA has been building these things since the 1970s. And the Valkyrie is actually the commercially licensed version of the NASA H-71M thruster, which is a best-in-class thruster. So some of the best experts in the field helped actually design this system, and now we're taking that design and turning it into a commercial product. And so this is the pointy end of the thruster. This is the thruster head. And if we could take this thing apart, you could see that there is electric power coming in, propellant coming in, and then you've got internally an anode and a cathode. And so the process by which we take a gaseous propellant, ionize that, and turn that gas into a plasma is through an interaction between that anode and that cathode. And so that's how you get the thrust. And that thrust is measured or created, goes up or down based on a variety of mechanisms. The first mechanism is how much power do you have going into the thruster head. That power is generated by an onboard source, usually a solar panel or an onboard battery, or in the future, maybe even a small nuclear reactor, and runs through this system here. This is called the power processing unit. And the power processing unit conditions all the power and then distributes the power to the thruster head, to the propellant management unit, to the engine controller, and certain other things. No, this is the brains also of the system, and again, this is the power processing unit. Redwire manufactures this for us. They are using basically all electronic SPI capability for the topology of this particular PPU. And obviously, this is the part that you want to make sure is radiation hardened, survives the outer space environment. This is the heart and the brains of the system right here. This part right here is the propellant management unit. Obviously, lots of tubing, valves, regulators, and things like that connected with the propellant tank. The propellant tank holds up to 3,000 psi of a noble gas, typically xenon or krypton, in some cases argon, will run through the propellant management unit, which then sets the flow rate for how much propellant actually goes into the thruster head itself. And so between the amount of power that you get from the power processing unit and the amount of propellant that goes through the propellant management unit depends on how much thrust your system can have. The Valkyrie is a best-in-class system. For 600 watts, which is the part that we're taking orders for now, it has the highest thrust from power ratio in any other 600 watt system. And so we got third-party validation that we're getting 34 millinewtons of thrust and about 1,350 seconds of ISP, which makes this an extraordinarily good thruster.
Thanks, Steve. So one of the interesting things you mentioned is propellant, and I find it fascinating that we talk about noble gases that we have to use, and you talked about krypton and xenon, xenon being the most prolific noble gas that's currently being used in a lot of the Hall effect thrusters today. But I'm noticing, I'm sure you're seeing a trend to an interest in krypton and how we can use krypton as effectively, knowing there's different atomic mass, which means there's different performance characteristics. What would you say is the major difference between the use of xenon and krypton, aside from cost, right? But using xenon and krypton obviously has significant advantages. So if you can tell me the biggest advantage and the biggest disadvantage, and for the rest of the audience that's listening.
Cost. So Xenon is an extremely good propellant. It stores the most densely. It gives you the greatest thrust per mass, and so you don't need a whole lot of it to get a mission done. Krypton, because it stores so less densely, you have to have a lot more krypton in order to get the same amount of total delta V for your propulsion system. And so that means you're going to have a much bigger tank, and that adds weight and size, to your thruster, which are budgets that you always want to carefully manage with a satellite. The other interesting thing, the other negative for krypton is these pole covers right here. They erode. This is one of the life limiters of a Hall effect thruster, is the pole covers right here. Xenon doesn't wear these things down that much. This particular system is basically good for 1.8 meganewton seconds, which means it's going to be up in space for a very, very long time. We can keep your satellite moving for quite a long while. That's on Xenon. Krypton will wear these down faster, and so one of the things that we're doing is developing different pole covers so that you get the same amount of longevity in krypton while simultaneously being able to achieve the extraordinary cost savings of krypton, but still use the same form factor of the same propulsion system.
One of the things that strikes me as interesting is if you're not familiar with Hall effect thrusters, you may think it's a giant system. Someone says, "Oh, you have a satellite thruster. How big is this?" Knowing when our system is put together, it's about 13 kilograms, right, in totality. But we have things in a disaggregated fashion here on the table where everything's individualized. Is that how we would put that onto a satellite, or what? Knowing full well that each customer is unique, we have non-recurring engineering functions and costs that have to go in. So how does Valkyrie enable customers with a variety of use cases, volume spaces, constraints, or maybe already pre-produced systems that they're like, oh, we got to fit this in. How do we do that with our system?
That's a great question, Jeff. A little bit of background to answer this well. Phase 4's got a cumulative amount of 18 years of flight heritage on our earlier thrusters. And with all that flight heritage, we've learned how to make a modular in-space propulsion unit. And so we can deliver this in any variety of ways. We can deliver it as a fully integrated system on a base plate that we just hand that to you, and you screw it onto your satellite where it needs to go. Or we can send you components and then help you integrate those components to meet your specific satellite bus design. And so that modularity also means that we have some advances in manufacturing where we can manufacture each of these things, have them on the shelf, and then when a customer comes in with a big order, then we just do the NRE with the parts that are already on the shelf, which means that we can deliver in as short as 10 months for a fully integrated propulsion system, or as little as 3 months for a kit of parts. And that puts us way ahead of the competition, who sometimes are telling their clients that, hey, we need 24 months to be able to manufacture these things.
One of the things you mentioned, which was interesting, was how the components are built, high quality, best in class. We're using a design from NASA, the H-71M design, but we have not just built it and said we're ready to go, right? We undergo a rigorous testing process. We just recently completed in the last few weeks a series of milestones and some significant tests. With not getting into too much technical detail, can you outline some of those high-level milestones and achievements that we made and exceeded, actually, right? I mean, some of these, talking with your technical team, was amazing of where we actually hit performance based off of predicted versus actual. Can you talk about that a little bit?
Yeah, absolutely. So we just wrapped up preliminary design review. We're well on our way to critical design review, which where we're basically going to be doing a lot of the environmental testing and building to make sure that this system, survives the shock of launch, the vibration of launch, survives the radiation environment in space, survives the extreme thermal changes, depending on where it's at in its orbit. Those are not trivial, but they also don't take nearly as long as achieving your PDR. And so we're already in low rate initial production for this system right now. We're building it to print the thruster head from the NASA design, so no changes at all there. One of the great things about this, getting back to the smaller weight and everything, is the H-71M has an inline cathode, which makes it much smaller than an out-of-line cathode. And so that reduces the size and the weight of the system. So you can see here it's like basically a big, thick hockey puck up there, which allows us to require less mass and less real estate on your system. That compactness also certainly helps with the vibration and shock testing. And so the great thing about having a phenomenal partner like we've had with NASA, and I really do want to stress that NASA's been an extraordinary partner with us on this, is that they've spent about 7 years making this design, and so our challenge was manufacturing that design. And so that made our challenge a little bit easier than if we started from a clean slate. But every time we tested anything, this is not hyperbole, this is a hats off to the engineering teams at both of our companies, that we hit the performance standard the very first time. So when Redwire gave us their PPU, it fired up effectively the very first time on all 8 set points that we had firing on both Xenon and krypton, very first time. I've never seen that before in space anywhere. When we sent this down to the High Performance Electric Propulsion Lab at Georgia Tech to get that third-party independent validation, you never want to grade your own homework. Very first time it fires, they collect data on it. Plume characterization, the plume is very tight, so your keep-out box is a lot smaller. And again, that's just a testimony to the high quality of the design and the design for manufacturing that NASA handed us off. But it's also just a attribute to the high quality of the engineers we have on the teams.
Just picking up on that thread right there, one of the we've been around, right? We've seen, the no plan survives first contact, right? No test plan runs perfectly the first time, and just picking up on that excellence in engineering from both of our companies to hook this up and then run through everything first time on Xenon and say, okay, we hit all of our test points. We still have this margin of time. We have, the craziness was, let's switch to krypton. Let's see what happens. And that just really doesn't happen unless you have really strong engineering, really strong quality control, really strong commitment to excellence from everyone involved. And I think it's really fascinating. When we talk about the thruster, what I really find interesting is that NASA designed this for actually interplanetary use. Right? This isn't designed for gentle, low ionizing radiation, low Earth orbit kind of things. This is a robust system that's designed to survive long duration in highly ionized environments. Can you talk just a little bit about how we can operate in any of these orbital regimes with high confidence, with minimal changes to design? It's a magnetically protected system. Talk just touch on some of those highlights.
Yeah, absolutely. The flexibility that the Valkyrie gives you is pretty extraordinary. For the same footprint, same thruster head, same PMU, all that sort of stuff, you can burn xenon or krypton. It's the only thruster out there that can do that. Typically, if you're going to switch from one fuel to another, you need a different thruster that's got a different footprint on your system. So if you want to launch and burn some xenon up front just to see how your satellite works, but then your intent when you scale that constellation is I'm going to switch over to krypton, you have the opportunity to do that without having to change your thruster out. And so that flexibility is pretty extraordinary. The second thing is the endurance, and we already talked about that. 1.8 meganewton seconds means that you're going to get a lot of total impulse out of this system, and it will keep you in space for a very, very long time. And can't get into the details of this, but that's why we have companies looking at hey, can this thing do cislunar? And the answer is yes. And so we're bidding on some cislunar missions with this system. The low Earth orbit environment is obviously a lot more permissive, and so that's within the tolerations of the system to do proliferated LEO. And then even more recently, we're looking at doing very low Earth orbit with this system as low as 200 kilometers. And for anybody who knows the VLEO environment, you got all kinds of problems with molecular oxygen, friction, and that sort of thing. But we believe that this system, given how robust the design is, straight from NASA, that it gives you that flexibility to be that same chassis underneath the car that you can put on just about any satellite and make that satellite go.
One of the, as we continue to look at what's going on in the space domain, you look at companies who are putting in these massive proliferated architectures. Obviously everyone thinks Starlink when that first comes up, but there's a lot of other companies who are looking at how they can put up multi-thousand constellations. Now, it doesn't take a super smart guy to figure out that there's a production capacity that exists within the current market of Hall effect thrusters. It's just like an automotive capacity. There's a set limit that it already exists. With the addition of these massive proliferated architectures, how does Valkyrie, Phase 4, and Redwire fill that need and serve those customers' mission sets for them to achieve their mission success?
Yeah, I can get religion on this, Jeff, and I'll try really hard not to, but space is getting super crowded. Back when a younger Jeff and a younger Steve were serving with, we were both majors at the time, serving with Major Chance Saltzman at the time, underneath Major General William Shelton. So dinosaurs were roaming the Earth. There were 850 satellites in orbit when we were at the Joint Space Operations Center. Today there are 14,000 active satellites and 3,000 dead ones and however many millions of space, pieces of space debris. All right. We used to get one, maybe two conjunction warnings a week. Now we're issuing 10,000 conjunction warnings a day. SpaceX had to maneuver their satellites on average about 275 times a day the first half of this year. So more satellites means we need more propulsion systems, but because you have to maneuver so much to avoid running into another satellite or a piece of space junk, each system is going to have to maneuver more often. And then you also have the policy requirement that you have to deorbit from low Earth orbit, or you have to supersync if you're going to be in geo orbit as part of trying to keep the space environment even operational. And so that means the amount of propulsion systems is going to be needed. Each one of those systems is going to have to do a lot more work, and then at the end of life they're going to have some oomph left so they can deorbit. And that is going to put a tremendous amount of stress on the supply chain for in-space propulsion. And so we have the capacity starting in Q2 of 2026 to roll about 22 to 25 of these off the assembly line a month. And so the great thing about partnering with a company like Redwire Space is that the limiting factor for most people who build Hall effect thrusters or any electric propulsion right now is power processing units. That is the pinch point within the pinch point of electric propulsion, and having a company like Redwire, PPUs are not going to be our gating manufacturing capability. And so we're very, very happy about that, and so we hope to make a dent in that overall demand. Conservative estimates are saying there's going to be about 60,000 more satellites in the next year or 5 years. Aggressive estimates are saying that there's going to be about 100,000 more satellites in the next 5 years. I read an article from the Congressional Research Service that was written in 2023 that stated that if every satellite that had been mentioned in a filing by a private company was actually launched, that there would be 1.1 million more satellites in orbit by 2035. Obviously, that's not going to happen, but think about the growth of assets on orbit. So you're going to be playing Frogger in orbit until you deorbit your satellite.
Yeah, well, thank you, Steve. Like I said at the beginning, working with old comrades in arms, getting back together again is always it's a reward in and of itself, but working on a system like this, best in class, enabling our customers to achieve mission success has just been, highlight of my career with Redwire so far, getting reconnected with you and your team, and I know our team working with yours, it's a thing of beauty. When things are working and everything's clicking. So I just want to thank you for taking time up here today. I'm going to wrap this up and just say thanks very much, and appreciate your time, and we're looking forward to helping our customers meet their missions. Thank you, Steve.
Thank you, Jeff.